Time to start the last talk this morning. Eyal Lubetzky from the Courant in New York will speak random walks and Ramanujan graphs, digraphs, and company.
Okay, is this on? Hi everyone. So I'd like to thank the organizers for the invitation. It's wonderful to be here. I'll be talking about two joint papers, one with Yuval Perez and the other with Alex and with Ori. And the work on Yuval is on graphs. The work with Alex and Ori is on digraphs and complexes. I was kind of hoping that Alex would cover the necessary background and that by this point everyone would already know what a building is. But what we'll do is, I guess we'll try to at least use a substantial portion of the talk in order to explain what we believe is happening, and then I'll try to give ideas of, we'll start with the picture in dimension 1 for graphs, and then we'll discuss the extensions. Okay, so unlike other talks, I'm going to start with the open problems. And these really are open. They are motivation. They are, maybe you can look at them as the motivation for the study, but we still do not know how to solve them. We know the answer. We just can't prove it, I think. Okay, so here is the Cayley graph from Avi's talk. I hope I didn't mess it up. Avi, this is the right one, right? I think it's one of the examples that he gave in his talk. So this is an expander. It's not a Ramanujan graph, but it is an expander, four regular. And here's a basic question. What can you say about the profile of distances? Okay, so take two random points or look at and tell me what the distance between them is. Okay, or what is the average distance in this graph?
FP.
What?
In FP. So Q is equal to Q squared. Q is a prime.
Q is a prime, yes. Q is a prime. Okay, so this is question number 1. Question number 2 seems kind of unrelated, but actually it's intimately related, and this is one of the themes that will be repeated in this talk. Understanding distances and the geometry, maximal distances, typical distances, goes hand in hand with understanding the behavior of various types, so the analogous types, the corresponding types, of random walks on your geometry. So you're running a simple random walk on this graph. It's an undirected graph. It's vertex transitive. It's the scaling graph, so it will converge. In particular, it's regular. It will converge to the uniform distribution, and the question is, how long will it take it to converge to the to equilibrium? This is question number 1 here. The second question is a little more delicate, and it's not how long it takes you to converge, but how do you converge? So is it the case that you slowly approach your equilibrium measure, or is it the case that for a long time you seem like you're stuck and getting nowhere, and then there's a sharp transition and all of a sudden you are essentially at equilibrium?
Even cutoff? No.
Yes. Yes. So that's exactly what I mean. Okay, so this would be abrupt, would be cutoff, and gradual would be no cutoff. Okay, so this was question number 1. What?
Any conjectures here?
Yes. Constant times log n. I don't know what the constant is. And abrupt transition. So for a long time, it will look like you are at distance. You will be at distance 1 minus little o of 1 in total variation from equilibrium. And then at that constant times log n, you will drop to distance 0. So this is the conjecture.
The simplest example is a simple random walk on the cube.
On the hypercube.
The hypercube.
Yeah, that's what happens there.
Coupon collecting, you just.
So coupon collecting gives you an n log n, and actually the cutoff is at half that, because you can miss square root, and the stationary distribution will not see the normal fluctuations of the last square root that you miss. But yes.
I just wanted to say that you're waiting till you see all the dimensions. I mean, that's a simple.
Yeah, almost all. Yeah. Okay. So this is what's supposed to happen here. We can't show it. We cannot show it. But it's kind of obvious that this has to be the case with such a nice graph. Okay, this is question number 1. Question number 2, let's consider a 3 uniform hypergraph. So David asked for an explicit example. Okay, I don't know if this isn't going to work. There is a graph on 80, what is it? 810 million vertices. Okay. Let's say that you can. There's a question about whether you want to see really an explicit construction for Ramanujan complexes or just for 2-dimensional expanders. Ori has an example for that we can plot out, but essentially, and it will be a relatively compact description. It will look something like this, only there would be many more matrices like that, and it will be a Cayley graph. And now the higher dimensional, the 2-dimensional expander will just be the clique complex over that graph. We'll just look at whenever you have a triangle, and that will be your hyperedge. So it will give rise to a 3 uniform hypergraph with bounded degree, and that would be an expander. Now, what is Ramanujan already requires a definition. But take such a thing, okay, and in this case, I'm referring here to the paper by Lubetzky, Beth Samuels, and Uzi Vishne from 05, and now do the same. Okay, now you have a hypergraph, and you can still ask about distances. So you have triangles in this hypergraph, and you can, for instance, this doesn't work. You can draw triangles like this, and ask how many triangles you need to glue, the smallest number of triangles that you need to glue to get from one vertex to another if they are chosen randomly. Okay, that's a natural question. You can also maybe glue them like that. So like either overlapping or disjoint or edge disjoint, like loose or tight. You can ask all these questions.
Loose is more or less the distance in the graph, right? Or by loose, you insist that it will be disjoint triangles, right?
Yes. Yes. I can't answer these questions yet for this, but we'll be able to say something along these lines. Okay, so these are still open. Any questions on the questions? Okay, so this picture of that looks seemingly unrelated about shuffling cards has a similar nature. You essentially all of these questions revolve around the same thing. We are just applying. We have some group in mind, and we're just applying some. We have a prescribed set of generators. We are applying them randomly, and we're asking how long it takes us to get either from one point to another or to approach equilibrium. Okay, and this notion that Michael already mentioned, cutoff, means that our convergence to equilibrium looks like essentially a step function. Okay, so we are at the maximal distance and then we drop to 0. Yes.
So what is that function, measuring? Like, what would be the line?
We'll get to it soon. Thanks for the question. Okay, so now let's start being a little rigorous. So deregular expander, this was already defined in previous talks, and so were Ramanujan graphs. And what we'll want to discuss in this talk, D will always be in this current talk, it will be the degree of regularity of the graph, and then I'll choose something else for the dimension. Okay, and if we look at this definition, we'll insist that Ramanujan graphs are connected, and I place it like this. I write that lambda has modulo either D, so I'm allowing it to be bipartite, so plus or minus, or in the interval of minus 2 square root D minus 1 and plus 2 square root D minus 1. here's a picture of Ramanujan graphs. This is the case of about 10,000 vertices, 6 regular. This is PSL2 F29 in the original paper of Lubetzky, Philip, Sarnak, and you see that the girth is huge in these graphs, and so everything is locally tree-like, and then once you exceed beyond the girth bound, essentially all hell breaks loose, and we lose our geometric understanding of what's going on, which poses a serious problem for the analysis. And this is a picture of the spectrum of 2 different Ramanujan graphs. One of them, the one with the spikes is the one from the previous slide. The multiplicity of each eigenvalue is huge. It's about what is it, Q, which is n to the 1/3 in this case. So polynomial multiplicity for the eigenvalues, and the nice flat one is just a random lift, going back to Nati's works many years ago. Okay, so this is a 1,000 lift of a small Peterson graph, just the Peterson graph. So these look kind of different. In the limit, the density it will still be Kesten-McKay, but what we're trying to understand really depends on quantitative properties of these eigenvalues. So even though these distributions look very different, the behavior of these objects that we're introducing in the opening slide should be the same. Okay, and I want to just mention related recent developments. So Ori's talk yesterday showed the connection between Ramanujan graphs and quantum computing, and so did Nasser's talk. And so in both situations, so we heard about both the connection to quantum computing and the new understanding of distances, typical distances and the maximal distance, specifically in Nasser's talk. Okay. So now we get back to your question, and I'm going to define this plot that I showed formally. What we'll be interested in usually throughout this talk, and this is what we typically are interested in, is to measure convergence to equilibrium via L1. Okay? And the reason that we're interested in L1, and you'll see a good example of that in this talk, is that L2, and essentially all the LPs for P larger than 1, these are analytic quantities that you can analyze in various cases, but they miss a lot of the properties that you can extract from knowing when the L1 cutoff really is, when one occurs. So in this situation, we use the equivalence, this equivalence, that tells you that total variation distance measures the worst distinguishing statistic between the 2 measures. So this is a very, very useful property. This is how we're going to extract geometric consequences from the knowledge of what the mixing time is. Okay. Now, for a Markov chain with a certain transition kernel P and stationary distribution pi, we just look at this total variation distance of the t-step probability measure starting from x to pi, and we wait for it to drop below some epsilon. Okay, so this is a monotone non-increasing function by let's say by maximal coupling or by Jensen's inequality. This will be true for any LP. At some point, it's going to drop below epsilon, and we're going to declare that point is the mixing is T mix of epsilon. That means that you reach equilibrium up to distance epsilon. And we'll be interested in the worst starting point, so maximum over all the initial positions. In our case, actually, most of the time, it may very well be the case that the graph is transitive, but in any case, we take a worst case starting position. And we say that cutoff occurs, so this goes back to Aldous and Diaconis in the early 80s. Also, this is Diaconis and Shashahani, Aldous, Diaconis. A sequence of chain exhibits cutoff essentially if epsilon doesn't matter. Okay, so T mix, it makes sense to say what T mix is even if you have a chain on 100 sites, just a finite chain. This notion already requires you to have a sequence of chain in hand. So there is some underlying parameter n, like the number of cards or the number of vertices in the graph. And we want to say that if you fix two precision parameters, epsilon and epsilon prime, and now you let the size of your system run to infinity, then it won't really matter which one of them you chose. The two quantities would be asymptotically the same. Okay, so 0.9 would be like 0.1. And that's exactly saying that this graph, which now I can tell you is just the total variation distance, starts at 1, goes down to 0, this graph drops abruptly. So this move from 1 to 0 is captured within the little o. Okay? Good. Okay, so now we can revisit this first example, this little Cayley graph. And what can we say about it? It is known to be an expander. Okay, Avi already mentioned it. This is an expander. And the fact that it's an expander essentially tells you that for any epsilon, your T-mix is sandwiched between two constants times log n. Okay? This first constant is just because you have a bounded degree. So you have to, before some constant times log n, you just see a tiny n to the delta fraction, n to the delta vertices. So certainly you are not close to equilibrium. This constant is a function of the eigenvalue, the spectral gap. By definition and by Chigger's inequality that we already heard about yesterday, you know that in L2 you will, at some constant times log n, you will drop to distance essentially 0. Okay, so certainly in L1, which is what we're measuring. So what we know is we have these two constants, and all the action happens in this interval. Okay, it's not like your convergence is going to extend gradually to infinity like a random walk on a cycle, which is like normalized properly. It's like Brownian motion. So you can never really, there is no single point after which you are at distance essentially 0. This isn't the case here. Here you have a single point, and you know that after which you know you are at distance essentially little o of 1. And the question is whether it looks like that, or whether maybe there are multiple steps, or maybe I don't know what. Okay, so this is what we don't understand. And the intuition tells you that maybe you could somehow take a couple of different expanders and create step functions, which you can do. It's actually not so hard. But the intuition tells you that if the graph is transitive, then you are not going to be able to do anything, and it's going to look just like a single step function that is at distance 1 and then drops to distance 0. So that's why we are convinced that in the opening slide that these questions, their answers are what we think they are.
So you think for every transitive graph?
Yeah, it's a conjecture of Perez from 04. We'll get to that, sir. Any transitive expander, any family of transitive expanders, this should be the case.
So for doubly transitive, do you know it?
Doubly transitive graphs are cliques or empty graphs?
No,
What?
okay, maybe
Okay.
Edge transitive.
Edge transitive.
Yeah, so just in the arithmetic combinatorics case, like the Bourgain, there are several works in which you have sort of pairwise independence, and once you get to a fixed power of the number of vertices, like n to the 0.9, then in 1 or 2 steps you are uniform. So this requires a very mild extension of transitivity.
This is when you add a plus a. And here
You have the fixed number. Okay, so that's good. So you have okay, good.
Okay, so let's focus on 3 bullets from this slide. First is that until 2010, we had essentially one example of cutoff on a bounded degree graph. Okay, and this proof, this is Lamplighter on ZN2. This used the estimates from the famous Annals of Math paper on the cover time of random walk on Z2. This used some very hard estimates. This work, but we need to compare this with a conjecture of Duret. It was floating around also in a previous paper with Bereshtiki, that on almost every 3 regular graph you should have cutoff. So the default is if you take a random deregular graph, it should have cutoff, but we couldn't prove it on essentially any example, almost. Okay? And until last year, we had no example of a transitive expander with cutoff. And this is the conjecture that I was telling Irit about, so that Perez made. I looked before, when I prepared the slides to this talk, I looked and I saw that around 2012, I was trying to push for people to maybe look at this into this conjecture. I gave maybe 3 colloquium talks that year, and in each of them I wrote at the last slide, conjecture of Perez on every transitive, show that on every transitive expander you have cutoff, and then question, is there any transitive expander where you have cutoff? And I would make the joke that usually when you make a conjecture on the entire family of graphs, it's after you saw 1, 2, 3 examples until you muster your courage to say that it's like that for the entire family, and yet we had no examples. So this was the case until last year. No examples, but still the conjecture was that it's for everyone.
What is the picture there on the slide?
Oh, it's the book of Duet. It's actually, it's a great random graph dynamics. It's kind of vague to see here, but okay. This is where he made the conjecture. Okay. Okay, so here are some more developments. There was this wonderful proof by Friedman of Noga's conjecture that almost every deregular graph is weakly Ramanujan, by which we mean that the second eigenvalue is essentially matching up to a little old term, the Alon-Bopana bound. And I'm putting this here because it's going to be a little relevant later on. And in 2010, and with Alan Sly, we confirmed the Duret's conjecture. So indeed, if you take a random deregular graph, it's going to have this sharp transition. Okay, this is for simple random walk. And what I mean by NB, this is non-backtracking random walk. This is an important element in this talk. So this is nothing but the Markov chain on directed edges of your graph, where you move from xy to a randomly chosen z that is not x. Okay? From every directed edge, you just kind of continue to the next directed edge, but you are not allowed to choose yx. And what we showed here was that actually if you do that, then your convergence is faster by a factor of d over d minus 2. Okay, so now what I write here, fast as possible, is also going to be a recurring theme. Why is this fast as possible? Let's look at the non-backtracking random walk. The degree, so the number of edges you can move to at every step is d minus 1, because we precluded one. Okay, so our covering tree, I mean, grows, the ball of vertices that we see grows at this rate. So if we look at 1 minus epsilon log d minus 1 of n, we see n to the 1 minus epsilon vertices, and certainly we're not mixed. So this is trivial. And the nice thing about it is that non-backtracking random walk is essentially mixed once you pass that point. And the same thing applies to simple random walk. If you think about this, just the fluctuations, if you walk, even if you were just never repeating vertices that you've already seen, and this is like a complete tree, the fluctuations of going up and down the tree mean that you go down with probability d minus 1 over d, and up with probability 1 over d, so your speed is d minus 2 over d, and you need the reciprocal of that to actually make it to the bottom of this tree. So even if this was a completely ideal situation where you just see new vertices all the time, you cannot beat this bound. And the simple random walk achieves it. Okay, so this is back in 2010. And we also had explicit constructions of expanders that had cutoff and ones that didn't have cutoff, but they were really tree-like. Okay, so far from being transitive. We wanted the ability to somehow manipulate what's going to happen to the walk. So we essentially built a tree and put an expander on its leaves, something like that. Actually, that's essentially what we did. Okay, and Shayan in 2015, I think in the context of some of another paper that we were working on, when Yuval gave a talk, asked whether it can be the case that Ramanujan graphs will always have cutoff. No. So transitive, not transitive, but just the fact that the Ramanujan should give such a strong constraint on the geometry that maybe you should have cutoff.
Did you use Friedman's result for it?
For this, no. No, the proof is elementary. It's and one of the things that at least that I was hoping to stress is that the way to prove something like this is essentially you want to say that if you just count the number of paths that emanate from X to essentially to almost all the other points, then you have the right number, which means that your mass kind of spreads evenly. It's essentially like walking on a tree, which and calculations of that form are doable in the random case because you can kind of expose the random graph as you go along, and things always fit nicely.
So yeah, since you mentioned it, what do you know about the LPS graph?
Just one last thing that I wanted to say in response to Doron's question. The nice thing is, and that's why I put Friedman's result here, is that here we looked at the randomness of the graph in order to count paths. Friedman used the paths, the control over non-backtracking walks, in order to control the second eigenvalue. And so there is this very close relation between the two, and this is also what, and I'm going to get back to that a little later, that's also what led us to re-examine Ramanujan graphs in this context, and somehow think that if you know that it's Ramanujan, then you should have enough power to control path lengths. What was your question, Michael?
What do you know about the LPS graph and the cutoff?
Before that, nothing. When I gave, I don't know, a colloquium in Tel Aviv University, also in Hebrew University, in a couple of years ago, I asked specifically, is there cutoff on LPS? Okay. So this is simple random walk, and it kind of looks like it's a graph. This is what it should look like. We have a blue curve and a red curve. This is L1 and this is L2. And I'd like to point out that there is a gap between them. Okay, for simple random walk. Okay, this is when you measure the L2 distance of your vector to the stationary one.
For random?
This is for GMP, right?
No. There's no G. This is for LPS.
What's log base 1 over P?
This is a rho,
Okay.
and rho is 2 square root d minus 1 divided by d. Okay. Good question. So this is a simulation, and this is what's actually going to happen. This is actually answering Michael's question, even though I didn't get to it yet. So this is the result with Yuval from 2016. We show that if you have a Ramanujan graph, then you have cutoff, including on LPS. It doesn't have to be transitive. The simple random walk essentially mimics the result of the random graph. Okay? Same location exactly.
And do you have it for LP, for every P as well?
We have it for LP for every.
You know the constant?
Great question. Wait with it just a second. I'll just say something very quickly. You don't really need the full power of being Ramanujan. It can be weakly Ramanujan, and you get the same thing. The little o is going to absorb the little o of weakly Ramanujan. And you can also allow some sub-polynomial number of eigenvalues to be, I don't know, 2/3 d, or anything that is less than d minus epsilon. They should be all uniformly, it should be an expander. Should be bounded away from d, but a sub-polynomial number can be way above the weakly Ramanujan bound, and the rest should be weakly Ramanujan. If you know that, then the proof works. Okay? So,
how important is that you are not bipartite?
It's not. If it's bipartite, then in the first step, you just you modify the first step to be lazy with probability 1/2, and then it's fine. So it doesn't. It applies in both cases. You just want to eliminate. This is to eliminate the periodicity, so I won't have to say what you just asked. Yes. Okay. Okay. So the LP. So in this slide, the message was that if you are doing a simple random walk on a Ramanujan graph, it's as fast as it can be. Because this is the delay of going up and down the tree. You can't avoid that. And this is essentially your radius of covering the vertices. So this is as fast as you can go. And the same applies for any LP. This is the definition of LP distance. It's a relative density with respect to pi, and you take sum over x, ptxy divided by pi y minus y to the power of p times pi of y. This is this notation. So if you measure convergence according to LP instead of L1, you have the same result. For any p larger than 1, Ramanujan graphs have the fastest LP mixing. Okay, out of and so there is LP cutoff, and it's in the best possible location, and these are the constants. Okay, you have asymptotically. Yeah, so this is what it looks like: L1, L2, L infinity. Okay, but I won't discuss LP anymore. I want to draw your attention to the graph distances. So here's a corollary. Remember that I said that you can extract a lot of information from the fact that L1 is synonymous with total variation up to a factor of 2. What does total variation tell us? It tells us that if we mixed, so past time log d minus 1 of n, okay, so this is actually a corollary of understanding the non-backtracking random walk. But in any case, suppose that you know that the non-backtracking random walk that just goes straight mixes at this time, log d minus 1 of n. That means in particular that you ought to see all the vertices by that point up to a negligible fraction. So in particular, your distance of any point, because we started from the worst case one, to almost every other point should be the right one, okay, which is what this says. And this was independently shown by Nasser using a different method, using Chebyshev polynomials. And also I'd like to point out the fact that the average distance of any 2 points is 1 times log base d minus 1 of n, means the diameter is at most 2 times that. Okay, this is easy because you take 2/3 and 2/3 and they intersect. Okay, so this bound is essentially the best known bound today, the best known upper bound on Ramanujan graphs. It matches the bound in this paper, again using Chebyshev polynomials of the other kind, I think. Peter, I think, conjectures it to be 4/3. But even getting a 2 minus epsilon for LPS, even getting a 2 minus epsilon would be dramatic. Okay, so question? Okay.
You could call this the observable diameter.
You could, but I call it the typical distance. Yeah. Okay. Here's one where it looks like already you are using more information on the graph than the previous slide shows. So I'm allowing you to look at a directed edge. So not just to start from a vertex, but to start from a vertex and go in a specific direction. And in these graphs, going in one specific direction can be deadly because the girth is huge. In order to turn around, you need to spend a constant times log n. And so even if you point out in a specific direction and you want to get to another edge in a specific direction, the distance is still the same. Okay? And specifically for LPS, for instance, you can find simple cycles of length exactly 2 log d minus 1 of n between any 2 points. Which means that, so it implies this, for one of the sides, that it's at most 1 times log d minus 1 of n. Okay, so you can, these are examples of various things that you can do once you know that these walks actually mix where they do. Okay, now, the key to our analysis was analyzing the non-backtracking random walk. the one that was featured in Friedman's paper that I mentioned before, and also his follow-up paper in order to understand lifts, and in Charles' recent work, Charles Bourdenay work from 2015. And so there they tried to bound, so to control the number of paths in order to get spectral information. We start with the spectral information and want to control the lengths of paths. So it's kind of a converse. Now, connecting the simple random walk to non-backtracking random walk is an elementary covering tree argument, okay, for these graphs. So this is something that you can ask me about later, but it's really, it's elementary. The point, I guess, is that already many years ago, when we try to understand the simple random walk on LPS graphs, what is the first thing that you can do when you have a graph and the information, the hypothesis is algebraic? The first thing to do is just to calculate what the eigenvalues actually give. And if you do that, you'll see that the distance of the walk to equilibrium, let's say that the graph is transitive, it's vertex transitive, and we're looking at the L2 distance to equilibrium. Then what you have is essentially, let's call it a lambda I. I'll put a tilde to say that I'm dividing by the degree. So these are the eigenvalues of the transition kernel, and I'm summing them from 2 all the way to n, and I'm raising them to a power 2t. Okay, at time t, it will be this. So I'm starting from 2 as opposed to 1 because 1 corresponds to the trivial eigenvalue 1 that I'm eliminating. That's my distance from pi. I have essentially this expression. Now, this expression, if you look at LPS graphs, a linear number of eigenvalues is going to be really close to the 2 root d minus 1, to the Alon-Bopana bound. This is Noga has a paper that gives a quantitative version of how many, and Ser has a so it's customary to, so, but Ser has a, is it really in a paper? I think it's yeah, it says, we also write Ser, but then okay, anyway, so epsilon n eigenvalues are going to be close to the edge. And so if you take, it doesn't really matter, so you have some epsilon n eigenvalues times that give you essentially 2 root d minus 1 divided by d to the power of 2t. And you want this big expression to be small. So what do you take? This guy, we called it rho. It's conveniently located here. So you need your rho, okay, to be your rho to kill the n, so your t should be 1/2 log base 1 over rho of n. And that's what that slide showed you. Now, what do you have as a lower bound? You have the usual bound that I just showed, the one where we kind of expose vertices as if it's a tree, the L1 bound. So the L1 bound is here. This is d over d minus 2 log d minus 1 of n, and that's that bound. And they differ. So this fails. Okay, we tried this many years ago. The nice thing about the non-backtracking random walk is that once you move to the non-backtracking random walk, then all of a sudden the L1 and L2 cutoff locations, each of them had cutoff. We couldn't show that this one had cutoff, but now we know that it has cutoff here. In L2 it has cutoff over there, and there's a gap. But for the non-backtracking random walk, eliminating the cycles caused these two guys to coincide for the non-backtracking random walk. I'll let you pick. This is the non-backtracking random walk in L1 and in L2. So we could sandwich the L1 as an upper bound by the L2, get cutoff here, and extract information on the simple random walk by the correspondence between the two walks. Okay. Now, okay, so I gotta hurry up. Okay, so what is the general principle? The general principle is that if you look at the universal cover, that covers it, for graphs it's just the tree, we had a walk that would bounce up and down. We precluded the possibility of going up by introducing the non-backtracking random walk. It can only descend. It never creates cycles. Doing that caused the L2 and L1 cutoff locations to coincide. So if we want to extend this to higher dimensions, here is what we think is going, this is what one could conjecture. If you take any random walk operator and look at it in the covering, in the analog of the covering tree, of the universal cover, which is now this complicated object that Alex was supposed to explain to you. Okay, this is the building. But this is just a generalization. There are, instead of lines everywhere, there are planes that have tilings on them, going like this in every direction, essentially. So you look upstairs, and there is this analog of the universal cover. And you look at a random walk operator there. And it's supposed to be the case that if you do not introduce cycles, or whatever the analog of this is a combinatorial condition here, that you did not introduce cycles here. Under the right condition that I mark as C here for cycles, it should be the case that if you have a Ramanujan complex, then that operator, its corresponding random walk, should have cutoff. So we look upstairs, we look at the behavior of the operator, and we can tell you that this operator is valid, and if you have a Ramanujan complex, like here you had a Ramanujan graph, then not only will you have cutoff, but L1 and L2 will coincide and so on, and it would be the fastest possible, and all good things are going to be guaranteed to you. Okay, and with Ori and Alex, we proved the version of this principle. The actual generalization that we had is that if you are walking on this building and you have an operator, we want it to be the case that there's a single, you look at the digraph that corresponds to this operator, like all the paths that it induces, and you want there to be a unique path or none between any two vertices. So if from every x, either you can never get to y, or you can get to y exactly in one way. And the same thing happens here. This is just a complicated way of saying it. Here you just always go down, it's just a tree. Here there may be forests, kind of directed forests, but this is a combinatorial condition. And the main result, this is what I'm not going to, this is the definition of a Ramanujan complex. You can glance at it for, let's say, 5 seconds. 1, 2, 3, 4, 5. I think that in Alex's talk there was only Heke instead of Ivahori. But other than that, this was roughly in his talk in one of the opening slides. Okay? And the result, okay, with Alex and Ori, is that if you take an operator and you look at this operator on the analog of the universal cover, of the tree that covers your finite Ramanujan complex. If this operator, you want it to be nice with the behavior, you want it to be equivariant. So you want it to behave nicely with respect to the group that you're acting on. Okay, so this is kind of an obvious condition. If it's collision free, this is what I should have emphasized. If it satisfies the combinatorial condition upstairs, that's the only thing that is required for you to say that if X is any Ramanujan complex, so X is the building mod gamma, is any Ramanujan complex, then you have cutoff and you have the distances guarantee, the typical distances. Okay, exactly as you had before. So we have an analog. Okay, and
It's the analog of the non-backtracking.
Yes. Yeah, it's the analog of the non-backtracking. And here are some examples. So we also have a sufficient and necessary condition in order to actually verify this combinatorial condition. But I gave a couple of examples here where you move from a triangle to another triangle, such that to a random kind of directed triangle, such that there is no triangle that joins x, y, and z. So in this case, it's from a directed edge to a directed edge. Here it's from a triangle to a triangle where they overlap. And you can read results like cutoff location, which and also tells you typical distances in triangles like that are disjoint, but overlapping just the vertex, or ones that are kind of tightly packed. Okay, and these specific operators were already studied in the context of zeta functions on Ramanujan complexes, and we can also, as a byproduct, confirmed what's called the Riemann hypothesis for these zeta functions, but that is beside the point. In the last minute, I just want to say something about the proof. The original argument in the paper with Yuval had essentially two ingredients in the proof. One, the main one, was the fact that goes back to Hashimoto using Ihara's zeta function that says that the eigenvalues of a non-backtracking random walk of this operator we're back to expanders, on a Ramanujan graph, all line up on the ball of radius square root d minus 1. It's in the complex plane. This operator is not normal anymore, but you can still look at the modulo of the eigenvalues, and all of them will line up here, except for the trivial one. Okay, so what does it mean that they line up at the ball of radius root d minus 1? Suppose that we go back to this exact formula, okay, this one, and we are ignoring the fact that this is not a normal operator, and that actually the eigenfunctions will also kick in. Let's ignore that, and let's suppose that this is diagonalizable and all the eigenvalues are exactly like that. Then I replace my lambda tilde, I replace it by root the modulo, so it needs to be like this in the complex plane. The modulo will just be root d minus 1. What is my degree? My degree is d minus 1. So I have 1 over root d minus 1 to the power of 2t. Okay? Which is just d minus 1 to the minus t, which fights an n. So my cutoff is at log base d minus 1 of n. So it's trivial. The problem is that this matrix is not normal, and with Yuval we showed that it's unitarily similar to a block diagonal matrix with blocks of size 2. So it was like this, and we calculated it. But if it's just 2 by 2, so it's almost normal. And the effect of these little blocks didn't really amount to much. That's how the proof worked in that paper. And what we do with Ori and Alex is generalize this to higher dimensions. And this is the last slide. And now there are two non-trivial steps. One is to show that you have a good spectral bound. So the analog of this Hashimoto, you want to say that that what you have is what Ori referred to yesterday as a Ramanujan digraph. You want to say that the degrees are essentially square root, that the spectrum is essentially inside the ball of radius square root the out degree. And the second is showing that it's blocked, that if your operator is good, then you can find then it's unitarily similar to a matrix that's block diagonal with bounded size blocks and bounded entries. And this is the essence of the new work. This is just an example for one of the operators that we showed in the previous slide. That's it. Thank you very much.
Any more questions?
Alex said yesterday, Alex promised this morning that he will show us something that you actually need Ramanujan property for.
Yes. Okay. So there's a question of defining what a Ramanujan complex is. I mentioned in the last slide that here there were two parts, right? A spectral and an algebraic. Okay. In order to say that the spectrum is the right one, you need to somehow, your input is just that the operator on the building is nicely behaved combinatorially. And now you want to say that on any finite quotient, if gamma is a co-compact lattice and so on, such that and B mod gamma is Ramanujan, you need to say that the spectrum of the operator on this finite graph is fine. And for that, you need to use the full power of what it means or what it means to be Ramanujan. And this goes back to the slide that I fast forwarded that said that relates the representations that you have downstairs to the representations that you have upstairs, and it says that they are weakly contained in L2 plus epsilon. And then you somehow need to also do some extra work in order to eliminate this epsilon, because
What
That's what you're asking about weekly Ramanujan as opposed to Ramanujan?
Graphs or about...
No, what Alex promised, he was trying to make a point that in some of the other works, you could replace the Ramanujan complex by a high-dimensional expander with certain other properties that are powerful, but they do not utilize the full power of being Ramanujan. I think that's what he was saying. And in this work, we need it.
For the proof.
For the proof.
Not for the result.
For the proof. No, it's probably true in...
But it's true that you can allow, say, plus, say...
Yeah. So as Ori said, so if it's weakly Ramanujan, then it will also work.
And it's tight in the sense there is an example of a graph which is barely not weakly Ramanujan and there is no cutoff there, correct?
It's not correct. I think, okay, it's correct
So
that
essentials being weakly Ramanujan.
there ought to be such an example. It's
You can handle some eigenvalues of that.
yeah, but if let's say that all of them are 2 plus epsilon and you are 2 plus epsilon prime, and now you want to say that you can, there ought to be such a counterexample, but nothing is published. And it's not. It's just conjecture.
I want to get back to this doubly transitive question. So the transitive question is open, I guess, still very interesting. There are properties of graphs. There's a version of doubly transitivity, but the simpler one for Cayley graphs is multiplicity of eigenvalues of second eigenvalue, high multiplicity of the second eigenvalue, which is used by Gowers, to show that when you are close to uniform, somewhat close, so Noga was right in the arithmetic combinatorics case, it uses for operators like A plus A, but what we are doing is A plus B, where B is a generating set. Anyway, you are just taking one step of a random walk.
Okay.
When you are close to uniform, you converge much faster than you converged before.
What is close?
Exactly. So in the arithmetic combinatorics case, because you're doing sort of A plus A, you're just whatever set you are uniform on, you convolve it with itself, then you need just to be a power of the size of the graph. Like if it's n vertices, if you are n to the 0.9 and you have this multiplicity or doubly transitivity, in one step you are uniform. Now in your case, you don't care about such things, and you also don't have such a big generative set, but you care about just moving from 1 epsilon.
Actually, the moving the. I want to say,
in this case,
I want to say that from 0.01 even, you move to...
Yeah, anyway, but you are close to your epsilon, so you are distributed, let's say on epsilon n vertices, you want to be distributed on 1 minus n. But uniformly, if you have this condition, I think the same general principle should give you faster convergence. So the Gauss paper, there's Babai, Piber, and
you have to be a bit careful because you also.
I'm just suggesting something.
No, it's a.
This is under, this Gauer quasi-randomness. So it works, for example, if you take a simple group of Lie, if the rank is bounded, you think mainly about groups like SL3P or P go to infinity. But what will happen if you will take SLP3 when it goes to infinity?
If you have this property, if you have high multiplicity of the eigenvalue or some doubly transitive, so you are saying in some cases it doesn't happen, so I don't care about it. Yeah. So a stronger condition than transitivity, I think, should.
And then your 0.9, is there some alpha that is associated with this 0.9, or is it the case that if you n to the delta for any delta, if I fix a delta and now let n go to infinity, if I'm at n to the delta, then in a few steps I'll get to.
I listened to your talk, I didn't do the calculations.
Okay. But so that's what we need.
Yeah, it even suggests possibly that the definition of cutoff could be even stronger than 1 plus little o 1, maybe between 0.1 log n and 1 log n, you just need a constant number of steps.
For the non-tracking random walk on the random graph case, it's order 1, the window. It is exactly like that.
Yeah, I have one comment about the profile of distances from an idea.
Yes.
As you mentioned, the diameter is less than 2 times the optimal one. So one may ask, what is the number of
Go back to your slide, yeah? Continue. Yes.
Yeah. So you may ask what is the number of points between with distance more than alpha times log, where alpha is between 1 and 2. We know it's 0 above 2. We know it's almost all around 1 plus epsilon. But what's going on in between? So by that variance argument, you can show...
Yeah, it's exponentially decaying.
They exponentially decay and...
yeah, it's also, I think...
exponent is interpolating between...
it's interpolating...
between 0 and 1. But one thing which I want to add is, in fact, this is true for all Ramanujan graphs. But if you restrict yourself to LPS Ramanujan graphs, then the exponent interpolates between 1 and the point 4/3. So you just move 2 to 4/3, and that's sharp under that heuristic assumption that I said. So it's quite nice that you can all count asymptotically the number of points.
It's not. It doesn't decay just like this. It should decay like this, d-1. That should be the exponent of your decay.
Sorry, what?
The exponent of the decay past 1 of the number of points, it should continue to look like this. So this is the way that you decay after 1. Maybe we're not talking about the same thing.
If you pick a generic Ramanujan graph, I
Still.
expect the diameter be 1 plus...
Diameter is different. For typical distances, I think that...
What I'm saying is for LPS, there are actually some points which have a distance...
some exceptional points related to your holes.
Yeah.
Okay. That is different.
Okay. So maybe we'll cut now the questions and leave it for later. And let me just remind you that maybe we should thank Eyal first.